Hi, welcome back. In this video, we're going to look at how to get a matrix representation for a linear transformation from an abstract finite dimensional vector space to another abstract finite dimensional vector space. So before we do that, let's review how to get the standard matrix for a linear transformation that just goes from Rn to Rm. So say we're given a linear transformation from Rn to Rm. The standard matrix for that linear transformation is going to be an M by N matrix whose columns are just the images of the N basis vectors, the standard basis vectors from Rn. So the first column of A is the image of E1, the standard basis vector. The second column is the image of E2, the third column is the image of E3, and finally the last column is the image of the last standard basis vector, En. And let's do a quick example to illustrate how that works. So say we have the linear transformation from R3 to R2 given by T of x, y, z is just x plus y, comma, x minus y. So we're given a vector in R3, and we can get a vector in R2. And this is a linear transformation, but let's find its standard matrix. So the standard matrix is going to be a 2 by 3 matrix. So the columns, there's going to be 3 columns, are going to be the images of the standard basis vectors in R3. So column 1 is the image of 1, 0, 0. Column 2 is the image of 0, 1, 0. And column 3 is the image of 0, 0, 1. So let's compute those images. So the image of 1, 0, 0 is the vector 1 plus 0, which is 1, comma 1 minus 0, which is also 1. The second column, we're going to compute 0 plus 1, which is 1, and 0 minus 1, which is negative 1. And then the last column, the first component is going to be 0 plus 0, which is 0, and the second component is 0 minus 0, so that's also 0. So this is the standard matrix for that particular linear transformation, and let's just check it out and make sure it does what it's supposed to do. So T of the vector xyz is supposed to be A times the column vector xyz. So let's do that multiplication and see what we get. So the first component is going to be 1 times x plus 1 times y plus 0 times z. So that's just x plus y. And then the second component is 1 times x minus 1 times y plus 0 times z, so that's just x minus y. All right, so it did what it was supposed to do. We got the right matrix. So now let's look at how we would get a matrix for a linear transformation from an arbitrary, abstract, general, finite dimensional vector space to another finite dimensional vector space. So if we have a linear transformation from V to W, and we know the dimension of V is n, and the dimension of W is m. So this is not Rn and Rm. These are just finite dimensional vector spaces. Then the matrix for this linear transformation relative to the two bases. So the first basis is B. That's a basis for the vector space V. That's V1, V2 up to Bn. And the second basis is B prime, and that's a basis for W. The matrix relative to these two bases is going to be this M by N matrix that we get by taking the first column is going to be the coordinate vector relative to B prime of the vector T of V1. So it's the image of the first basis vector in B but we take the coordinate vector of it relative to the other basis b prime. And then we do that for the second column. The second column is the coordinate vector relative to b prime of the image of the second vector in the basis b. And we keep doing that until we get the last column. The last column is the coordinate vector relative to b prime of the image of the last vector in the basis b. All right, let's see how this looks on an example. So in this example, we have a linear transformation from P2, the vector space of all polynomials of degree at most 2, to P1, the vector space of polynomials of degree at most 1, and the transformation is just the derivative, or the differential operator. So you take a polynomial of degree at most 2, you differentiate it, and you get a polynomial of degree at most 1. So these are finite dimensional vector spaces. Remember, the dimension of P2 is 3, and the dimension of P1 is 2. So if we use the standard bases for R3 and R2, we can use coordinate vectors. So let B be the standard basis for P2, and let B prime be the standard basis for P1. We're going to find the matrix for this linear transformation relative to the two bases, B and B prime. So first, we're going to write down the bases. So the basis for P2 is just 1x and x squared. The basis for P1 is just 1 and x. And so now what we're going to do is we're going to compute each of the columns of the matrix we're looking for. So the first column is going to be the coordinate vector relative to B prime of the image of the first basis vector in B. So that's the polynomial 1. So we're going to find t of 1 and then find the coordinate vector relative to B prime. And then the second column is going to be the coordinate vector relative to B prime of the image of the second basis vector in B. And then the third column will be the coordinate vector relative to B prime of the image of the third vector in the basis B. So the first one, t of 1, is the differential operator d sub x of 1. But we're finding the coordinate vector relative to B prime. The second one is going to be the coordinate vector relative to B prime of d sub x of x. And the third one is the coordinate vector relative to B prime of d sub x of x squared. And remember what the differential operator is. We're just taking the derivative. So the derivative of 1 is 0. But we need to find the coordinate vector of that polynomial relative to B prime. To do that, to find the coordinate vector relative to B prime, we need to write the polynomial 0 as a linear combination of the vectors in B prime. So B prime consists of the vectors 1 and x, and so we can write 0 as the linear combination 0 times 1 plus 0 times x. And then the coordinate vector relative to B prime of that polynomial is just the vector where the components are just the coefficients in that linear combination. So that coordinate vector relative to B prime of the polynomial 0 is the vector 0, 0 in R2. All right, so let's do that for the second one. The derivative of x is 1, but we're going to find the coordinate vector relative to B prime. So we rewrite 1 as a linear combination of the two basis vectors in B prime. So that's 1 times 1 plus 0 times x. And then we just pull out those coefficients and write down the coordinate vector. So the third one, the derivative of x squared, is 2x, but we need to find the coordinate vector relative to B prime. So we rewrite 2x as a linear combination of 1 and x. So 2x is 0 times 1 plus 2 times x. And then the coordinate vector of that relative to b prime is just the vector whose components are the two coefficients, 0 and 2. All right, so we have found the 3 columns of our matrix. So we can write down the matrix A is the matrix whose first column is 0, 0, second column is 1, 0, and the third column is 0, 2. And you can check to make sure that this is actually the differential operator by just taking any old polynomial in P2, find its coordinate vector relative to the standard basis for P2, multiply that coordinate vector by the matrix A, and see if you get the coordinate vector relative to the standard basis for P1 of the derivative of the polynomial you started with. All right, so try that, and I'll see you in another video.